imagine an artificial mind that is so um, incredibly complex and so relentlessly driven to solve the exact problem you've given it that it can literally think itself to death.
Yeah, it's a pretty intense way to look at it.
I mean, it is. If it tries to hold, just one too many thoughts in its working memory, or if it explores one too many parallel possibilities, its digital universe physically collapses.
Right. It simply ceases to function.
Exactly. And today, we are looking at the foundational architecture of an AI system that is so heavily constrained by the laws of physics and computational limits that it actually has to drop tombstones to learn from its own deaths.
Which is just a fascinating survival mechanism.
It really is. It does all this just to survive long enough to give you an answer. So, welcome to the deep dive. We have our hands on a truly unprecedented document today.
We really do. It's an incredibly dense, highly mathematically rigorous architecture deconstruction report.
Yeah, and it's for a system operating under the codename Claude code. And our mission today, just to be clear, isn't to talk about what this AI can write or, what apps it can build for you.
Right. No, we're going much deeper than that.
Way deeper. We are going to translate the topological maps, the Markov chains, and these thermodynamic barriers in this report into a clear, jaw-dropping blueprint of exactly how this system thinks at a structural level.
And, we are not going to shy away from the hard mathematics here.
No, we really can't.
Right, because to truly understand this architecture, you have to realize that the math isn't just some theoretical abstraction.
It's the literal reality of the system.
Exactly.
Hmm.
In the system, the formulas act as the physical laws of its universe. Just as gravity dictates the orbit of a planet, these equations dictate the flow of this machine's consciousness.
Oh, wow.
Yeah, and the report explicitly defines the system at its objective level as a resource-constrained multi-agent state machine.
Okay, let's unpack this because that is a massive, intimidating string of words.
It definitely is.
But the report gives us something even more profound right up front. It offers what it calls the ultimate essential definition of how this entire system operates.
Yeah, this is the core of everything.
Right. It defines the mechanism as, and I'm quoting the report directly here, local negentropy evolution within constrained state space.
Such a powerful phrase.
Let's pause right there because I feel like if we don't understand that phrase, the rest of the architecture will just look like noise.
Yeah.
What in the world is negentropy?
So to understand negentropy, we actually have to start with entropy, which is a foundational concept in thermodynamics.
Okay, I remember that from high school physics, I think.
Right. In physics, entropy is the measure of disorder or randomness or chaos in a closed system.
Right, the universe moving toward chaos.
Exactly. The second law of thermodynamics essentially states that the universe is always moving toward higher entropy. Like if you drop a glass coffee mug on a tile floor, it shatters into 100 pieces.
Right, an absolute mess.
Yeah. The system has moved from a state of high order, a structured, useful mug, to a state of high disorder or high entropy.
And it's not going to fix itself.
No, the universe will never, ever spontaneously reassemble those shards of glass back into a mug on its own.
Right, chaos is the default setting of reality.
Exactly. So negentropy, which is just shorthand for negative entropy, is the active, deliberate reversal of that process.
Okay, so building the mug.
Right. It is the destruction of chaos and the creation of order, structure, and useful information. But here is the catch, and this is crucial. Negentropy does not happen for free.
It takes effort.
It requires work. It requires energy. Biological life is actually the ultimate example of a negentropic system.
Oh, that's an interesting way to put it.
Yeah. A living cell takes in chaotic, raw nutrients from its environment, burns energy, and uses it to maintain its highly complex, ordered internal structure.
And when it stops?
When a cell stops consuming energy to fight off entropy, it dies and chaos wins.
So the designers of this architecture are explicitly stating that this AI system is functionally a digital organism.
That is exactly what they're implying, yes.
Like you give it a chaotic, unstructured problem, say, a massive folder full of broken, undocumented code, and its entire purpose is to act as an engine that consumes computational energy to force that chaos into ordered negentropic structure.
Precisely. But the second half of that definition is just as critical. the part that says within constrained state space.
Right, the constraints.
The system does not have infinite energy. It does not have infinite memory. It is building a castle of order, but it only has a limited number of bricks, a strict time limit, and a very specific plot of land.
Oh, wow.
If it wastes its energy exploring dead ends, or if it tries to hold too many variables in its head at once, it hits a thermodynamic wall and crashes.
That raises a huge structural question then. If I give this AI a massive, sprawling task, let's say I drop a 10,000-line Python application into its lap and say, find the memory leak and rewrite the network protocols.
Which is a huge task.
That is an ocean of chaos. If the AI tries to load all 10,000 lines, all the dependencies, and all the possible solutions into its single stream of consciousness at once, won't it immediately violate that constrained state space and die?
Yes, it absolutely would.
So how does it even begin to tackle a problem larger than its own working memory?
It does it by recognizing that it cannot do it alone. The system relies on an architectural concept called Distributed Directed Acyclic Graph Computational Offloading, or DAG offloading for short.
Okay, DAG offloading.
Yeah, it relies on the illusion of infinite compute. The AI you are talking to is not actually the entity that does all the heavy lifting.
Wait, really?
Really. The primary intelligence acts as a master node called the coordinator. When you hand it that massive Python codebase, the coordinator doesn't start reading line 1.
What does it do then?
Instead, it analyzes the request and breaks the macro problem into a web of highly specific microtasks. It then spawns entirely separate child nodes, known as workers, to handle them.
Okay, I want to map this to something tangible. It sounds like the coordinator is acting like the lead architect on a massive skyscraper project.
That's a great way to visualize it.
Right, because the lead architect doesn't put on a hard hat, grab a trowel, and start laying bricks. That would be catastrophic waste of their cognitive overhead.
Exactly.
Instead, they look at the master blueprint, realize they need a foundation, plumbing, electrical, and drywall, and they break those into separate jobs and hire independent subcontractors, the workers, to execute them.
That is a highly accurate analogy. And the system doesn't just hand these tasks out randomly either. It organizes them into a directed acyclic graph.
The DAG part.
Right. The directed part means the workflow has strict one-way dependencies, like
Yeah.
the electrical wiring cannot be finalized until the structural framing is complete.
Makes sense. And the acyclic part?
That part is crucial. It means there are no cycles, no loops. You can never have a situation where task A requires task B to finish, but task B also requires task A to finish.
Oh, an infinite loop.
Exactly. That would create an infinite deadlock, which in a resource-constrained system is a fatal waste of compute.
So the coordinator maps out this perfect flowing river of dependencies. But how does it mathematically determine the cost and structure of this delegation? Because spawning a worker isn't free, right?
It absolutely is not free. Every worker consumes memory and processing budget. The report gives us the exact formula the master node uses, which is called the compute offloading matrix.
Okay, let's hear the math.
It looks like this. The metatask matrix, represented as a script m submeta of t, is equal to the sum from I equals 1 to n of omega sub I multiplied by worker sub I of c sub I, plus a final function called s sub synthesize.
Okay, let's break that equation down so we can hear what it's actually doing. It starts as a sum, so we are adding up the cost and output of every single worker from the first one to the nth one.
Correct.
What is the omega sub I that sits in front of each worker?
So the variable omega sub I represents the individual computational weight or the complexity of that specific subtask.
Like how hard the job is.
Basically, yeah. Searching a single text file for a keyword is a very low-weight task. It requires almost no cognitive effort. But compiling the entire codebase and running a full suite of unit tests is a massively high-weight task.
Oh, I see.
The coordinator assigns this omega sub I weight to accurately predict how much of its total resource budget this specific subcontractor is going to burn through.
That makes perfect sense. It's budgeting. But then we get to the worker function itself, worker sub I of c sub I. The report places a huge emphasis on that c sub I variable.
It really does.
It defines it as independent context isolation, and it specifically highlights two operational modes, spawn fresh versus continue.
Why is context isolation so critical for an AI? Why not just let all the workers see everything the coordinator sees?
Well, if you let a worker see everything, you completely defeat the purpose of offloading. You just recreate the exact same cognitive overload you were trying to avoid.
Oh, right, because they have limited memory, too. Exactly. Think about your 10,000-line Python example. If the coordinator needs a worker to just check the syntax of one specific 50-line function, Giving that worker the context of the entire 10,000-line code base is highly inefficient.
It's just noise to them.
It clutters the worker's short-term memory. It might even start hallucinating connections between the small function and a totally unrelated part of the code it read.
So Spawn Fresh is essentially giving the subcontractor temporary amnesia.
That's a good way to put it. Spawn fresh means C sub I is zeroed out. The worker wakes up in a void. It knows absolutely nothing about the user, the overarching project, or the history of the conversation.
It's just a blank slate.
Exactly. It is handed only the 50 lines of code and the instruction. Find the syntax error. It applies 100% of its neural processing power strictly to that microtask, solves it, and returns the answer.
Wow.
It is incredibly fast and highly objective because it has no preconceived notions.
But surely there are tasks where amnesia is a bad thing, right? Like, if I need a worker to write a new feature that seamlessly integrates with the rest of my app's specific architecture, a blank slate worker wouldn't know what my architecture even looks like.
And that is exactly when the coordinator chooses the continue mode for C sub I.
Oh, okay.
In this mode, the worker inherits a carefully curated subset of the master node's memory. It understands the tone of the user, the broader architectural goals, and the ongoing conversational context.
So it's more expensive to run, but necessary.
Right. It takes more compute, but it allows for nuanced, integrated work. The brilliance of the compute offloading matrix is that it mathematically balances these two states across dozens of simultaneous workers.
Which brings us to the very end of that equation. We added up all these workers, some with fresh memories, some continuing the context, all with different weights, and at the end we add S sub-synthesize.
Yes, the dimensionality reduction synthesis function.
Right. The report calls it that. What does it actually do?
Well, if we return to the architect analogy, imagine the end of the workday. 50 subcontractors walk into the architect's office at the exact same time and dump 50 massive binders of raw data onto the desk.
That sounds like a nightmare.
It is. Every single receipt, every chemical breakdown of the concrete, every minute-by-minute time card. If the architect tries to read every page, their brain will crash.
They need an executive summary.
Precisely. S sub-synthesize is the mathematical executive summary. High-dimensional data is data with thousands of variables in raw tokens. Dimensionality reduction compresses that data down to its core vectors.
So it strips out the fluff.
Exactly. The master node takes the thousands of tokens generated by the workers and forcefully extracts only the actionable conclusions, like the foundation is poured, the syntax error is on line 42, the test passed.
That is so elegant.
By doing this, the coordinator updates its own master state without overflowing its highly constrained memory.
Okay, so the coordinator is constantly launching workers and compressing their results. That sounds like a chaotic, high-speed orchestration. How does the system even know if it's succeeding?
That's a great question.
Like, how does it monitor its own brain power without, ironically, using up all its brain power just to monitor itself?
That is a profound engineering problem, actually. The report details a performance observer system utilizing tools called StatStore and fpiece metrics. But the elegant core of this monitoring is the state measurement function, which relies on the reservoir sampling algorithm.
Okay, let me set up the problem here, because I think it highlights exactly what you mean about physical constraints.
Go for it.
The AI is processing a continuous high-velocity stream of telemetry data, how fast the workers are, how much memory is being used, API latency. It has no idea how long this task will run. It could take 2 minutes, or the user could keep giving it follow-up prompts for 2 weeks.
Right, the length is unknown.
But the report says it has a hard physical boundary of limited memory, mathematically defined as k equals 1 till 24. It can only hold exactly 1,024 pieces of performance data in its monitoring pocket.
And if it tries to hold 1,025, the array overflows and the monitoring system crashes.
Right. So if I'm a naive programmer, my first instinct is just to keep the most recent 10,024 events, a moving window. As a new metric comes in, I throw away the oldest one. Why wouldn't the system just do that? It seems so much simpler.
A moving window is disastrous for objective system analysis.
Really? Why?
Because if you only keep the last 10,024 events, your AI has zero memory of its past performance. Imagine the system hits a massive, catastrophic latency spike in hour 1, but then runs smoothly for the next 10 hours.
Okay.
By hour 11, that catastrophic spike has been pushed entirely out of the moving window. The system looks at its current 2024 items, calculates its cognitive load, and concludes, I am running perfectly.
Oh, wow. It becomes completely blind to long-tail anomalies and structural degradation over time.
Exactly. It's recency bias baked right into the math. It forgets its trauma just because time passed.
So how does the reservoir sampling algorithm fix this? The formula the report provides is the probability of x sub I being in the reservoir equals the minimum of 1, or the fraction k over n.
This algorithm is a masterpiece of resource-constrained mathematics. Let's translate it. P is the probability that a brand new piece of performance data, x sub I, will be kept and placed into the reservoir.
Okay, got it.
K is our hard limit, our pocket size of 24. And N is the total number of events the system has ever seen since it woke up.
Ever seen.
Right. The probability of keeping a new item is the absolute minimum of two values, the number 1 or the fraction K over N.
Let's run a simulation in our heads to see how this actually behaves in real time. The system wakes up, the very first chunk of data arrives.
Right, N is 1.
N is 1.
Yeah.
Our fraction is 124, divided by 1, which is 124. The formula asks for the minimum between 1 and 1024. The minimum is 1, so the probability is 1, or 100%. We keep the data.
And that logic remains identical for the first 124 events. As long as the total number of events, N, is less than or equal to our pocket size, K, the fraction K over N will always be 1 or greater.
Because the numerator is bigger.
Exactly. Therefore, the minimum will always be 1. The system effortlessly saves the first 124 metrics without throwing anything away.
But the thermodynamic wall is hit the exact millisecond the 126th event arrives.
Precisely. Let's do the math on that one.
Okay, event 125 hits the stream. Now, N is 125. The fraction is 124 divided by 225. That number is roughly 0.999.
Right.
The minimum between 1 and 0.999 is 0.999. So now there is a 99.9% chance we keep this new piece of data.
Correct. And if the system's random number generator hits that 99.9% probability, it accepts the new data. But the pocket is full.
So what does it do?
It randomly reaches into its pocket of 124 existing items, pulls one out, permanently deletes it, and replaces it with the new one.
Now let's fast forward. The AI has been debugging this code base for 3 days. Millions of microtasks have run. Let's say N is exactly 1 million.
Okay, a huge number.
The 1 millionth piece of telemetry arrives. The fraction is now 1,024 divided by 1,000. That's about 0.001. The minimum is 0.001. There is now only a 0.1% chance that this new data gets kept.
And this is where the profound mathematical beauty reveals itself.
It seems like it's just ignoring new data, though.
While it seems like the system is heavily biased against new data as time goes on, the algorithm mathematically guarantees that at any given moment, every single event that has ever occurred from event 1 to event 1 Melzen has the exact same equal probability of currently being in that reservoir of 124 items.
Wait, really?
Yes.
The first event from 3 days ago has the exact same chance of being in the pocket as the event that happened 2 seconds ago.
It mathematically preserves a perfectly uniform, unbiased sample of its entire lifetime, all without ever exceeding 124 items in memory.
That is just wild.
It's incredible. It can accurately calculate its P50, P95, and P99 cognitive load over infinite time, bounded entirely by strict finite physics.
Wow. Okay, so we've established how the system monitors itself and how it delegates complex tasks in the present tense. But an AI doesn't just exist in a single snapshot of time.
No, it has to progress.
Right, it has to take a user's prompt, interact with tools, read files, and march forward through time to arrive at a final answer. So how does it conceptualize its own journey through reality?
To understand that, we actually have to look at the foundational axiom of the entire architecture. This is what the report calls the core computational theory.
Okay.
It's based on the autoregressive, partially observable Markov decision process.
Autoregressive, partially observable Markov decision process,
Yeah.
or POMDP. That sounds like something straight out of a theoretical physics textbook.
It is quite a mouthful.
Let's pull that apart, because I know classical Markov decision processes, or MDPs, have been used in AI for decades.
They have. A standard Markov decision process is a mathematical framework used to model decision-making in situations where the outcomes are partly random and partly under the control of the AI. The absolute defining characteristic of an MDP is the Markov property. The Markov property states that the future depends only on the current state of the world and completely ignores the history of how you got there.
The classic analogy is a game of chess, right?
Exactly.
Like, if you and I are playing chess and I suddenly leave the room and an AI takes my place, the AI doesn't need to know the sequence of the last 40 moves.
It doesn't care.
It doesn't need to know if I aggressively sacrificed my queen or blundered a knight. It only needs to look at the exact current position of pieces on the board right now.
Oh.
The current state contains 100% of the information required to calculate the optimal next move.
Exactly. A standard MDP requires the system to be able to see the entire chessboard. But Claude code operates in a PUMDP, a partially observable Markov decision process.
Largely observable.
When you drop this AI into a massive code base, it does not get to see the whole board. It is functionally blindfolded.
Oh.
It doesn't know what files exist. It doesn't know what functions call other functions. It doesn't know the directory structure. It only has limited, localized visibility.
So it has to take actions just to figure out where it is. Like, it has to run a tool like the else command just to see the files in the current folder before it can even formulate a plan to edit them.
Right. And because it is partially observable, the strict Markov property completely fails.
Because the current state isn't enough.
Exactly. If you only look at the current instantaneous state, like a blinking cursor in an unknown directory, you have absolutely no context. To survive, the system relies on the first word of that massive title, auto-regressive.
Meaning it regresses or looks back on itself.
Yes. Instead of relying solely on an instantaneous snapshot of reality, the AI builds its reality by relying on its own monotonic historical trajectory. It maintains a perfect sequential ledger of every single action it has taken and every single piece of feedback the environment has given it.
And the report provides the exact mathematics for how this ledger is built. It's called the trajectory evolution equation.
Yes, a very important formula.
This formula represents the literal mathematical flow of the machine's consciousness over time. The formula is cow sub t plus 1 equals cow sub t, a plus the set of m subassistant of a sub t, a plus the set of m subtool result of e of a sub t.
It looks intimidating on the page, but it is functionally just a diary. Let's walk through it.
Please do.
Tau sub t, or the Greek letter tau at time t, represents the entire sequence trajectory up to the current moment in time. It is the massive text transcript of everything that has happened since you gave it the initial prompt.
And the equation shows us how we step forward into the future to the next moment in time, tau sub t plus 1.
Right.
So we take the current diary, tau sub t, and we apply this specific operator, the circle with a cross in it, the a plus symbol. The report defines this as vector concatenation.
And this is a critical design choice. Concatenation is an append-only operation. You're taking a string of data and gluing new data strictly to the very end of it.
Okay, let me play devil's advocate here for a second. An append-only memory sounds like a terrible design flaw.
Why do you say that?
Well, it means the AI can never actually delete a mistake.
Right.
Right. If it explores a dead end, it's just dragging its failures along with it forever. Why not let the AI edit its past? If it tries a piece of code and it fails, just erase the failure and pretend it never happened. Why force this strict concatenation?
Because if you allow the AI to edit its past states, you trigger what is known in computer science as the dimensionality explosion paradox.
Oh, it sounds bad.
It is the curse of dimensionality that destroys classical MDPs. If an AI wants to look 5 steps into the future and it has 10 possible actions at each step and it can constantly alter its past conditions to create new alternate realities, the number of possible environmental states it has to calculate grows exponentially.
Right, the math gets out of control.
It jumps from 10 to 100 to 1,000 to 100,000 parallel universes. The computational math literally explodes to infinity and the system freezes.
But by using vector concatenation.
By using strict append-only concatenation, the system flattens the multidimensional complexity of reality into a single one-dimensional timeline.
That's brilliant.
It doesn't have to model 100,000 parallel universes. It takes its current action, a sub t, and maps it into discrete text tokens using the m subassistant function.
Okay, so if the action is running a script, that text gets glued to the diary, then the environment responds. Maybe this script throws a traceback error. That environmental feedback, E of A sub t, is mapped into text using M subtool result, and that also gets glued to the very end.
So it's just reading a single document.
Exactly. The AI only ever has to read its own linear diary to know exactly what reality it is in.
It's an incredibly elegant solution to an infinite math problem. But, and this brings us to one of the most terrifying concepts in the report. This elegant solution creates a deadly physical trap.
Yes.
The AI is constantly appending to its diary, growing its context sequence linearly. But the universe it lives in is finite. The report calls this the resource constraint axiom, or the thermodynamic barrier. Yes, the math governing this barrier is absolute and unforgiving. The system evaluates 2 strict inequalities at every single time step.
What was the first one?
First, the sum of the cost of all tokens from the beginning of time to the current moment t must be less than or equal to b sub max.
The maximum budget. This is the financial thermodynamic limit.
Correct.
Every single token the AI reads or writes consumes a fractional amount of electrical compute power on a server farm somewhere, which translates to a fractional amount of human currency. If the AI gets confused and enters an infinite loop of executing the same broken script, it is burning real money.
Exactly. And if the sum of that cost breaches B sub max, a max budget USD exception is thrown. The system is instantly executed. It is a hard kill switch.
Wow. But the second inequality is the one that really threatens the AI's cognitive process.
Right, the spatial limit.
It states that the total physical size of the sequence trajectory, size of tau sub t, must be less than or equal to W sub context window, the context window.
This is the boundary of working memory. Even if you have infinite money, modern large language models can only hold a finite number of tokens in their active neural network at one time.
So there's a physical ceiling.
If the append-only diary gets too long, if the AI spends too much time reading huge error logs or exploring complex directories, the length of tau sub t hits that ceiling.
And what happens if I'm human and my working memory gets full? I just get a little confused. I lose my train of thought. What happens to this AI?
It triggers a prompt too long exception, and just like the budget limit, it is lethal.
Lethal.
The system physically cannot process the next step. The architecture report explicitly refers to breaching this barrier as a catastrophic collapse of the state machine.
So if you've ever been using an AI to help you code, and you've been going back and forth for an hour, pasting in huge blocks of text, and suddenly the AI just stops or throws an error or seemed to completely forget what you were talking about, it didn't just decide to ignore you.
No, it hit a wall.
It hit a thermodynamic wall, it reached the absolute limit of its universe, and died. Which means, if this architecture is going to actually function for long, complex tasks, it must have a survival mechanism.
It absolutely has to.
It must have a way to avoid suffocating under the weight of its own growing memory.
And it does. To survive, the system relies on topology-based memory compaction. It has to look at its own append-only diary and violently compress it.
Violently compress it.
Mathematically, it treats this survival mechanism as a variation of a classic computer science dilemma known as the knapsack problem.
Okay, let's unpack the knapsack problem for anyone who hasn't taken a discrete math class recently.
The great analogy.
The classic analogy is that you are an explorer. You have a knapsack that can hold exactly 50 pounds of gear. You are standing in a treasure room filled with hundreds of items, gold bars, ancient artifacts, rare gems.
Right.
Each item has a specific weight and a specific dollar value. Your goal is to pack that knapsack so that you maximize the total dollar value you carry out without exceeding the strict 50-pound limit. If you try to pack 51 pounds, the knapsack rips and you get nothing.
It is an optimization problem under strict constraints, but in the Claude code system, this isn't about treasure, It's about cognitive survival.
Okay.
The knapsack is the small amount of space remaining in the context window before it hits the lethal barrier. The items are the individual nodes of memory, the questions, the code snippets, the tool results that make up its history.
And the value.
The dollar value is the information leverage or the entropy reduction value of that specific memory. The AI has to prune low-value information to make room for its next thought.
The report defines the objective function of this compaction process. The AI is trying to maximize the sum of I of m sub I multiplied by x sub I.
Let's translate those variables. M sub I represents a specific memory node in its history. I of m sub I is the calculated information value of that node.
Give me an example of that.
Sure, a massive raw text dump of a useless file might have a very low I of m sub I. The final synthesized realization of where a bug is located has a massive I of m sub I.
Got it. And the x sub I.
X sub I is the binary decision variable. It is a simple switch. 1 means the AI chooses to keep the memory in the knapsack, and 0 means it permanently deletes it.
So it's maximizing the total retained value, but it is subject to the physical constraint. The formula states that the sum of the size of the tokens, token of m sub I, multiplied by x sub I, must be less than or equal to theta subthreshold minus delta subsnip.
Right. It calculates exactly how much space it needs to free up to get below the danger threshold, theta subthreshold.
And the delta snip.
It subtracts a safety margin, delta subsnip, to ensure there is actually enough empty space left over for the AI to actually generate the text of its next action.
Now, here is where my mind was completely blown. If I'm building this compaction algorithm, my first instinct is FIFO, First in, first out. Just delete the oldest messages. When the knapsack gets full, delete the conversation from 3 hours ago.
Yeah.
Why doesn't the AI do that?
Because strict chronological deletion destroys the semantic integrity of thought.
How so?
Well, if the AI deletes the initial prompt you gave it because it's the oldest memory, it might be in the middle of writing a brilliant piece of code, but it suddenly has absolutely no idea why it's writing it. It becomes a ship without a rudder.
Okay, so maybe chronological is bad. What if it just strictly follows the knapsack objective? It just looks at the I of M sub I scores, the value of each item, and ruthlessly deletes everything with a low score to keep only the highest value insights.
That is even more dangerous, actually, and the architecture explicitly forbids it using a topological constraint.
Oh, really?
Yes. The report says this constraint is necessary to correct the absence of causality. It gives us the specific mathematical condition. For all M sub j, right arrow M sub I in dA, it implies X sub j is less than or equal to X sub E.
Let me trace that logic, because it's really dense. We have the universal quantifier, the for all symbol. For all situations where memory node J points an arrow to memory node I. The arrow means a strict dependency, right?
Yeah.
Node J is the prerequisite and node I is the result.
Yes, a perfect example. Node J is the AI invoking a tool asking, what is in this directory? Node I is the tool's response. There is a file called config.json.
Okay.
The answer node I is entirely dependent on the question node J.
So if that dependency exists, the math demands that X sub J must be less than or equal to X sub I. Let's test that constraint. Remember, the X variables are switches, either 0 or 1. Let's say the AI decides that the answer, config.json, is incredibly high value. It wants to keep it. So X sub I becomes 1.
Now look at the constraint. The math states X sub J must be less than or equal to 1, which mathematically means X sub J could be 0 or it could be 1. But wait, if the AI chooses X sub J equals 0, what just happened?
If X sub J is 0, it means it deleted the question. The AI kept the answer but deleted the memory of asking for it.
Exactly. And the architecture recognizes this as a catastrophic failure of logic.
It breaks causality.
Right. The optimization algorithm is heavily penalized if it ever creates a state where X sub I equals 1, meaning keeping the dependent node, but X sub J equals 0, meaning deleting the prerequisite.
Wow.
The system structurally enforces that if you keep the result, you must keep the context of how you got that result. The report calls the violation of this rule a semantic topology graph fracture.
Semantic topology graph fracture. I've been thinking about this like packing a parachute into a knapsack.
Oh, I like this.
You're analyzing the value of your gear. You look at the massive nylon canopy of the parachute and realize it has extremely high survival value. So you pack it. Then you look at the tiny metal ripcord. By itself, a piece of wire doesn't seem very valuable. If you just follow strict value optimization, you might throw the ripcord away to save weight.
But you can't.
Exactly, because the canopy is functionally useless without the ripcord. They are causally linked. If you fracture that graph, you die.
That is a perfect, visceral analogy. The AI's thoughts are structurally bound to respect causality. If it remembers the answer 42, the mathematics strictly enforce that it cannot delete the question, what is 6 times 7?
It's defending the integrity of its own mind.
Yeah.
And while it is fighting this thermodynamic battle internally, the architecture report reveals it also has to defend itself externally.
Yes, the UI layer.
Right. It has to survive the messy, unpredictable reality of interacting with a human user interface.
Yeah.
The report introduces the concept of spatial collision detection and UI event penetration blocking.
This represents a shift from the deep back-end mathematics to the literal geometry of the user's screen.
Geometrically.
Yeah, when a human interacts with an autonomous system, maybe a graphical terminal, they are a source of chaos. They might click random buttons, hit the escape key, or trigger conflicting inputs simultaneously while the AI is trying to execute a delicate operation.
Humans are entropy.
Exactly.
Yeah.
The architecture has to manage this spatial chaos.
And again, my instinct as an amateur programmer would be to write a polling script.
Right.
I'd tell the AI, every millisecond, check layer 1 to see if it's receiving input, then check layer 2, then check layer 3. But the report calls the actual method reverse thinking.
Polling is computationally expensive. If you constantly ask 100 UI elements if they're being touched, you are burning your resource budget.
Right.
Instead, the architecture uses spatial folding on the z-axis, the depth of the screen layers. It doesn't pull for inputs. It defines the absolute boundaries of rejection.
The formula for this blocking boundary determination is modal active equals there exists an O in overlays, such that O is not in non-modal overlays, which implies block of input lower layer.
Let's read that geometrically, it asks. Does there exist an active screen overlay, O, that is not classified as a non-modal overlay?
A modal overlay is a window that demands complete dominance. Like when you try to close an unsaved document and a tiny box pops up saying, "Do you want to save?" You physically cannot click anything else on the screen until you address that box.
Exactly. The formula says that the moment a modal overlay exists, the implication is triggered immediately. Block input, lower layer.
So it just shuts everything else down.
The architecture drops a mathematical dead zone over everything beneath it. It doesn't need to turn off every individual button on the lower layer or constantly check their status. The spatial geometry of the modal overlay itself physically intercepts and neutralizes any input event trying to penetrate it.
It's like dropping a massive physical glass shield over a control board. You don't have to individually wire every switch to the off position. If a human slams their hand down, they just hit the glass. The input never reaches the system. It's computationally cheap and perfectly impenetrable,
It is absolute spatial defense.
which naturally leads us to the ultimate defense mechanism of the architecture. It's one thing to defend against a clumsy human clicking the wrong button, but what about malicious code?
That's a whole different threat.
What about an AI that hallucinates and tries to delete the entire file system? We are talking about an autonomous, multi-agent system executing code on a machine. The security sandboxing has to be flawless, and the report tackles this with something it calls the Boolean algebra-based interceptor chain.
The security section of this architecture report is deeply philosophical. It connects its sandboxing methodology directly to one of the most famous foundational problems in all of computer science: the halting problem.
Alan Turing's halting problem. Now, I know the broad strokes of this. Turing proved mathematically that it is impossible to write a general computer program that can analyze any other arbitrary program and determine with 100% certainty whether that second program will eventually finish running and stop, or if we'll get stuck in an infinite loop and run forever.
That is correct. The halting problem proves that global universal prediction of code execution is fundamentally undecidable. You cannot know what a complex system will ultimately do until you actually let it run.
So if it's impossible to predict what code will do, how on earth do you build a security sandbox for an AI that writes and executes unknown code?
You do it by abandoning the arrogance of global prediction. The architecture explicitly relies on the local decidability of the halting problem.
Local decidability.
It doesn't try to solve Turing's impossible puzzle. When the AI decides to run a Python script, the security system does not scan the script and try to predict if it will loop forever or what its final output will be in 20 minutes.
So what does it evaluate?
It only evaluates one microscopic, instantaneous question. Does the very next proposed action touch a predefined lethal boundary right now?
It's like a bouncer at a high-end nightclub.
Ugh.
The bouncer doesn't try to psychoanalyze you at the door to predict if you're going to have a few drinks and leave quietly, or if you're going to start a brawl at 2 a.m.
Because that's undecidable.
Right. Predicting your entire night is the undecidable halting problem. The bouncer just looks at your ID right now. Are you on the banned list? Yes or no? Local decidability.
A very precise, localized analogy. The architecture implements this bouncer using the permission filtering tensor. The set of allowed tools, tool sub-allowed, is defined as any tool T where there does not exist a rule R in the deny rules that matches T.
But the security goes way deeper than just deciding which tool the AI is allowed to use. It evaluates the exact parameters the AI passes to those tools, and this is where the path security topological proof comes into play.
This is critical for file access.
Right. If the AI asks to read a file, it passes a file path. The security system runs a piecewise function called f_subsafe of path sub_raw to determine if that path is lethal.
Let's decompose f_subsafe. The function returns true, meaning the AI is allowed to access the file only if two strict conditions are met simultaneously. First, real path of path sub_raw must be a strict subset of real path of dir subteam.
Okay, path sub_raw is what the AI typed. Dir subteam is the designated safe sandbox directory where the AI is supposed to be working.
Yeah.
So the system takes whatever weird string the AI generated, resolves it to its absolute actual location on the hard drive, and verifies that this final location exists entirely within the borders of the sandbox. It stops the AI from wandering into the system folders.
But the subset check isn't enough. The second condition, connected by a logical AND, requires that the raw path must not contain specific character strings. The formula explicitly bans 3 strings, .. /0, and the %sign.
Why These three specifically. What is so inherently dangerous about two dots?
These represent classic, devastating attack vectors that bypass standard subset checks. The double dot is the command for directory traversal.
It means go up one folder level.
Right. An attacker or a severely hallucinating AI might construct a path like sandbox save folder password.
Oh, I see.
The system might see the path starts with sandbox and think it's safe, but the double dots dynamically walk the execution up and out of the sandbox to read sensitive system passwords.
Sneaky. What about /0?
That is the null byte. In lower-level programming languages like C, a null byte literally tells the computer, this is the end of the text string. Stop reading. If a security system is checking a file extension and an attacker inputs malicious script.shay/0.txt, the security system might read the whole string, c.txt at the end, and approve it as a harmless text file.
But the computer reads it differently.
Exactly. When the underlying operating system executes it, it hits the null byte, stops reading, and executes malicious script.she.
Wow. This is a syntactic cloaking device. And the percent sign.
The percentage sign is the core of URL encoding and format string vulnerabilities. It can be used to obfuscate the other attacks, encoding a double dot so the basic scanner doesn't even recognize it.
The report states that if Serve Subsafe detects any of these conditions and returns false, it triggers an absolute isolation sandbox truncation. What does that look like? Does it warn the AI, like, hey, you use a double dot, try again?
No, there are no warnings. There are no second chances. It is an absolute, immediate termination of the execution thread. The bouncer doesn't argue with you. You are thrown onto the street.
That is brutal.
And this level of absolute paranoia isn't isolated to one check. The architecture enforces these rules through interceptor cascading.
The mathematical formula for the cascade uses that massive wedge symbol, the big A and D symbol. V sub hook pass equals the big A and D from I equals 1 to N of not prevent continuation of hook sub I.
The massive wedge is the mathematical symbol for a logical A and D gate applied across an entire set. It means every single security hook, from hook 1 to hook N, must be evaluated sequentially. Hook 1, A and D, hook 2, and D, hook 3.
And the not prevent continuation part.
That function means the hook analyzed the action and found absolutely no reason to stop it.
So for the action to pass, hook 1 must be clean, Andy, hook 2 must be clean, hook 3 must be clean.
All of
If you have 50 security hooks, and 49 of them say the file path is perfectly safe, but one single hook detects a hidden null byte and returns true for prevent continuation, the entire cascading A and D gate instantly evaluates to false. The action is vaporized.
It is an architecture built on absolute mistrust of its own generative outputs. It must mathematically prove safety at every millimeter of its progression.
Which is incredibly robust. But it brings me to a really critical question about the fragility of the system. We just talked about how absolute the security is. We talked about how hitting the thermodynamic token limit instantly kills the threat.
Yes, death is everywhere in this system.
Right. So what happens when the security does trigger? Or what if the AI tries to call an external API and the internet connection just briefly drops? If every single error results in catastrophic termination, this AI would never finish a complex task. It would just constantly die.
That is the ultimate tension of the architecture, and it is resolved by the fault-tolerant routing topology, or, more philosophically, the mathematics of resurrection.
The mathematics of resurrection.
The system expects to die. It expects the environment to fail. It is designed as a robust topology within a nonlinear dynamical system.
The report states that when an extremum boundary probing fails, meaning the AI pushes against the edges of its reality and breaks something, the current state subtree collapses. The immediate thought process is violently destroyed.
Yes.
But the macro system survives by triggering the state evolution piecewise function, represented as pi of tau sub t plus 1.
This function determines the exact mechanism of resurrection based on the specific nature of the death. It calculates the next trajectory using 4 distinct bifurcation states dictated by a variable called epsilon, which represents the error state.
Let's walk through the 4 states of reality this machine can experience. The first is the baseline. If epsilon equals 0, there is no error. The system is in a survive state. The piecewise function simply returns execute of a sub t.
The machine takes a step forward. But let's look at the first collapse scenario. What if epsilon equals e submodel fail?
When does that happen?
This occurs when the underlying large language model simply glitches. It hallucinates or it returns a response in a broken JSON format that the system cannot parse.
The function dictates that it returns retry of tau sub t, model sub fallback. It doesn't just blindly hammer the exact same action again, hoping for a different result.
No, that would be madness.
It actually rolls its consciousness back to the last safe trajectory, tau sub t, and it invokes a fallback model.
It degrades its own complexity to prioritize stability. If the cutting-edge, highly creative model fails to format its output correctly, the system hands the context to a smaller, less creative, but strictly deterministic fallback model to force the action through.
Okay, state 3. What if epsilon equals E sub token limit? This is the thermodynamic barrier we discussed earlier.
Yeah.
The memory knapsack is completely full.
This is a severe collapse. The function returns compact of tau sub t, which leads to execute of a sub t.
So it pauses.
It halts all forward momentum. It triggers the topologically constrained knapsack algorithm, painfully prunes its own memories while defending its semantic causality, and only after sufficient space is cleared does it attempt to execute the action again.
It performs emergency brain surgery on itself. But the fourth state is the one that is truly haunting. What if epsilon equals E substream abort?
This is the most profound one.
This happens if a critical network stream severs, or if the human user physically hits the cancel button mid-thought. The function returns rollback of tau sub d minus 1, all plus tombstone.
The tombstone. This is one of the most profound concepts borrowed from distributed database architecture.
The architecture report includes this incredibly poetic, almost literary line right in the middle of all this dense math. Physical time is irreversible, but the computational axis can transform destructive collapse into controlled degraded reconstruction through local resets and tombstone records.
It's a beautiful line.
Explain the tombstone to me. Why is it necessary?
Imagine the AI is a mouse navigating a maze. It runs down a corridor, turns left, and hits a literal brick wall, a dead end. The execution collapses.
Okay.
If the AI's only recovery mechanism is to roll back its memory to the moment before it turned left, if it completely erases the memory of the mistake, what is going to happen?
It's going to wake up at the intersection, look at the left turn, and because it has no memory of the pain, it's going to turn left again. It will hit the wall, die, roll back, and turn left again. Forever. It enters an infinite loop of death.
Precisely. If you erase the memory of the failure, you guarantee the repetition of the failure. To survive, the rollback cannot be a perfect erasure. A tombstone is an intentional, permanent entropy increase record.
So it leaves a mark.
When the system rolls back to tau sub tit minus 1, it forces a tiny, undeletable martyr into its own context window.
It drops a breadcrumb of its own corpse. It sacrifices a precious sliver of its highly constrained working memory to leave a permanent warning sign for its future self. I tried to call this API with these exact parameters. It resulted in death. Do not do it again.
It manufactures evolutionary pressure within its own execution loop. The tombstone structurally forces the AI to explore new state spaces, to turn right instead of left, because the path to the left is now mathematically weighed down by the probability of collapse. It learns from its own death.
But if the system is dropping tombstones and adjusting its future behavior based on past traumas, that implies a level of memory that goes beyond just the immediate active context window.
It does.
If the AI is working on a massive project for a month, it can't keep every single tombstone or architectural decision in its short-term memory. The knapsack would overflow immediately.
And that transition leads us directly to Section 6 of the architecture: long-term memory retrieval and context injection. The system utilizes a time-decayed attention mechanism to interact with its non-volatile storage.
Let's contextualize this. When a specific task cycle ends, the AI can extract vital static entities, maybe the user's coding style preferences, or a fundamental rule about the database schema and save them to a long-term hard drive.
Right.
But if you run this system for a year, that hard drive is going to contain thousands of memories. When the user asks a brand new question, how does the AI decide which memories to pull from the hard drive and inject back into its short-term consciousness?
It cannot read them all. So it calculates a joint distribution of relevance and time decay using a heuristic relevance score. The architecture explicitly notes that this heuristic approach was chosen to correct the abuse of strict Bayesianism.
Let's look at the mathematical formula for how it assigns a value to a memory. First, it calculates the age of the memory in days. Delta t sub days equals the floor of t sub now minus t sub time divided by 86,400,000.
That is simply the delta of time. T sub now is the current timestamp in milliseconds. T sub time is the timestamp of when the memory was originally created.
So it just finds the difference.
You subtract them to get which is exactly the number of milliseconds in a 24-hour day. The floor function, the brackets, simply rounds down to the nearest whole day.
Okay, so we know how old the memory is. Now we plug that into the main relevance equation. Relevance of m sub given query equals sigma of cosine of query comma m subdesk multiplied by e to the negative lambda times delta t subdays.
Let's dissect this. The first half of the equation, sigma of cosine of query comma m subdesk, handles semantic similarity. The system takes your current immediate question the query and converts it into a high-dimensional mathematical vector, essentially an arrow pointing in a specific direction in a multidimensional concept space.
Okay, I'm visualizing the arrow.
It does the same for the description of the stored memory, m subdesk. It then calculates the cosine similarity, which is the angle between those two arrows.
So if I ask a question about how to optimize a database index, and there's a memory from last month titled SQL Database Indexing Rules, those two vectors are going to be pointing in almost the exact same direction. The cosine similarity will be very high, close to 1.
Correct. The sigma applies a sigmoid function to smoothly normalize that score. So purely based on topic, the memory is highly relevant. But then the architecture multiplies that topical score by the second half of the equation, e to the negative lambda times delta t subdays.
Time decay.
This is the exponential time decay factor.
This is where the age of the memory weaponizes against it. Euler's number, E, is raised to the negative power of the memory's age in days, multiplied by lambda, which is a tuning constant for how fast memories should fade.
Because it is a negative exponent, as the days increase, the value of e to the negative lambda times delta t subdays collapses exponentially towards 0.
Even if the topic matches perfectly.
Even if the cosine similarity is a perfect 1.0, if the memory is a year old, the time decay multiplier will crush the final relevance score to a tiny fraction.
I have to say, it feels incredibly organic. It models the fading ink of a human diary. If you try to remember what you ate for breakfast, the memory from yesterday is vibrant and accessible. The memory of breakfast from 3 years ago has a massive time decay. It's almost impossible to retrieve.
Unless...
Right, unless you got violently food poisoned 3 years ago. That trauma would create such a massive, overwhelmingly high cosine relevance to the concept of breakfast that it would overpower the time decay and force its way back into your consciousness.
It's exactly how the math behaves. And the report notes that this heuristic time-decayed approach is a deliberate rejection of strict Bayesian updating.
Why reject Bayesian logic? Isn't Bayesian probability the gold standard for AI logic?
In a theoretical vacuum, yes. A strict Bayesian system attempts to calculate the exact mathematical posterior probability of every single possible hypothesis by updating it with every single piece of historical data it has ever seen.
Sounds thorough.
For a simple system, it's perfect. But for an autonomous AI operating in a complex code base, strict Bayesianism requires evaluating thousands of cascading probabilities across years of data. It is computationally intractable. It would freeze the system.
It's the dimensionality curse again.
Exactly. The time decay heuristic is a computationally cheap approximation of biological memory. It is good enough to survive without burning the entire resource budget.
So it scores all these memories, and then what? How do they actually influence the AI's next move?
The system utilizes the prior injection iteration formula. Prompt sub t plus n equals prompt sub base plus the union of m sub I for I in top k.
It takes the base prompt you just gave it, and it glues the union of the top K memories directly into the context window. It takes the 5 or 10 memories with the highest heuristic scores and literally pastes them into the AI's short-term memory before it is allowed to think.
The architecture notes that this injection converges the random walk scope of the next multidimensional search. By injecting past knowledge, past tombstones, past architectural decisions, the AI does not have to start from scratch.
It's not stumbling in the dark.
It doesn't have to wander aimlessly. The injected memories act as guardrails, narrowing the search space and immediately pointing the AI in the most probable direction of success.
We have journeyed so far into this machine. We started with a master coordinator spinning up a web of amnesiac workers, carefully monitoring their cognitive load with a mathematically perfect reservoir.
We really have covered a lot.
We watched the AI step forward in time, writing its append-only diary, constantly terrified of the thermodynamic limit of its context window. We saw it violently prune its own memories to survive, physically block chaos on the UI layer, and navigate the halting problem with paranoid cascading interceptors.
And we saw it die and drop tombstones?
Yes, we saw it die, drop tombstones, and retrieve fading memories from the past. But what is the culmination of all this effort?
The culmination is Section 7 of the architecture, the process lifecycle closed loop and state persistence. The system ultimately acts as a dissipative structure.
A dissipative structure.
Right.
Another concept pulled directly from non-equilibrium thermodynamics. What does it mean in this context?
The physicist Ilya Prigogine won a Nobel Prize for his work on dissipative structures. They are complex systems like a hurricane, a whirlpool, or a living cell that maintain their highly organized internal structure by constantly exchanging energy and matter with their chaotic environment.
They feed on chaos.
They take in high entropy, process it, and dissipate the chaos, leaving behind localized order.
And Claude code is fundamentally a mathematical dissipative structure. When I give it a vague, chaotic prompt like build me a web server, it enters a state of high entropy search. It spawns workers, it hits dead ends, it drops tombstones, it hallucinates, it rolls back.
It burns computational energy to navigate the chaos.
But its entire architectural purpose is to force that chaos into a low entropy deterministic state. It collapses all that multidimensional potential into a single, perfectly structured text file.
We see that collapse mathematically in the terminal convergence function, result equals psi of tau sub final. When the AI's trajectory sequence finally reaches a terminal state, the system evaluates it.
And what does it output?
If valid of tau sub final is true, the system outputs the structured code and the delta of the resources it consumed. If it is false, it outputs the diagnostic error data. But either way, the chaos has been resolved into a concrete result.
And that result feeds into the final macro-level equation of the entire report, the cross-cycle metadata evolution. Engine state sub k plus 1 equals engine state sub k opulus transcript write opulus memory extraction.
This is the completion of the closed loop. The macro cycle k is finished. To prepare for the next cycle, k plus 1, the system takes its overarching state, concatenates the linear transcript of everything that just happened, and extracts the vital entities to its long-term, time-decaying memory.
The report phrases the final result beautifully. By exchanging energy and information with the external system, the current closed loop is completed, outputting the entropy reduction of the current cycle as the initial deterministic input for the next state machine lifecycle.
It's a perfect summary.
It consumes the chaos of your vague prompt, burns electrical energy on a server, and outputs a highly ordered code file. And then, tomorrow, that ordered code file becomes the stable foundation for your next, even more complex prompt. The negentropy scales. It evolves.
It is the ultimate manifestation of the definition we read at the very beginning. Local negentropy evolution within constrained state space. It is an engine designed to systematically destroy digital chaos.
Which leaves me with a final, somewhat haunting thought for you to ponder. We just spent an hour dissecting the cold, hard mathematics of an artificial state machine. We looked at the topologically constrained knapsack problem. We looked at the heuristic relevance score. We looked at the mathematically enforced tombstones.
It is all rigid, physical, thermodynamic limitation.
But look at the behaviors those equations produce.
It produces a system that prioritizes deeply relevant memories but allows the distant past to fade. It produces a system that experiences trauma, drops a tombstone, and alters its future behavior to avoid the paths that caused it pain.
It produces a system that actively filters out cognitive overload so it can focus on the task at hand.
It mathematically models behaviors that we almost exclusively associate with organic, sentient experience.
We like to think of our own human intuition, our gut feelings, our fading memories, our avoidance of past mistakes as something magical, something uniquely biological. But if this artificial system relies on time-decayed algorithms to filter its past and tombstones to learn from its deaths, at what point does a heavily constrained mathematical state machine begin to functionally resemble the physical constraints of the human mind?
Maybe our magic intuition is just a time-decayed relevance score operating inside the thermodynamic constraints of our own skulls. It is a profoundly provocative question, and it underscores exactly why deconstructing this architecture is so important. We are no longer just building faster calculators or better search engines. By forcing these systems to survive within physical constraints, we are inadvertently modeling the fundamental mechanics of thought itself.
And what a journey into those mechanics it has been. Thank you for joining us on this incredibly deep dive into the architecture of tomorrow. Keep wondering, keep challenging the boundaries of the chaos around you, and we'll see you next time.